The Webb glance extends so far out that it captures light that has been traveling for over 13 billion years yet. The universe has been expanding, and thus, the light has been stretched for the most distant worlds we're looking back. In time nearly to the Big Bang, the immensity of the universe might seem vast, but every bit of it originated from what we refer to as the singularity. Currently, this is our interpretation of the Big Bang Theory. However, the James Webb Space Telescope, JWST, has revealed significant mysteries about the universe's birth and development, leaving us astonished. Prestigious physicist Brian Cox has declared that the remarkable discoveries made by the JWST might actually reshape our entire understanding of the universe. Join us as we delve into these new celestial discoveries that promise to transform our comprehension. The James Webb Space Telescope, named after the esteemed NASA Administrator James E. Webb, stands as a mark in modern galactic investigation. This telescope represents a significant technological leap forward from its predecessor, the Hubble Space Telescope, resulting from a collaborative effort between NASA, the European Space Agency, and the Canadian Space Agency. The JWST surpasses the capabilities of its forerunner. It utilizes cutting-edge technology and a design optimized for studying the universe in extraordinary detail. Unlike Hubble, the JWST conveys clear and sharp images of distant celestial bodies operating primarily in the infrared range. This unique characteristic allows it to penetrate astronomical dust and capture celestial objects that were previously hidden from our view. With its massive 6.5 m primary mirror composed of 18 hexagonal segments, the JWST dwarfs Hubble's reflector size. Situated approximately 1.5 million kilometers away from Earth at the second range point L2, it orbits the Sun in sync with Earth, ensuring a steady and continuous view of the universe while looking into the distant corners of the universe. It involves exploring light years, but also a form of time travel. The JWST uses infrared instruments to observe celestial objects and events going back billions of years. The light emitted by these objects due to the expanding universe undergoes redshift, shifting from the visible range to the infrared frequency. Fortunately, the JWST can detect infrared light emitted by celestial bodies at extreme distances, enabling researchers to study the birth of stars, investigate galaxy formation, and examine exoplanet atmospheres. Its latest historic discovery involves identifying an incomprehensible mass of galaxies at the edge of the observable universe. This finding challenges the validity of the prevailing theory of how things came to be, prompting a reassessment of our fundamental cosmological assumptions. To better understand how we arrived at this point, we should take a short journey through the history of space investigation. Early civilizations like the Greeks and Chinese laid the foundation for understanding planetary movement by observing celestial bodies. Newton's laws in the 17th century provided a theoretical framework for space travel. In the mid-20th century, Edwin Hubble, an influential astronomer, made historic revelations in cosmology and observational space sciences. His observations revealed that distant nebulae were isolated galaxies far beyond the Milky Way, transforming our understanding of the universe's size and expansion. Hubble's law, established by him, showed that galaxies farther away were receding at higher speeds, providing evidence for the expansion of the universe. The post-World War II era of space exploration marked the beginning of the space race, with the Soviet Union Sputnik in 1957 as the first artificial satellite in orbit, Yuri Gagarin's orbital trip in 1961, and the Apollo 11 moon landing in 1969 were crucial accomplishments. Fast forward to 1990, when the Hubble Space Telescope was launched, providing exceptional clarity and stunning insights into the universe. The journey from ancient observations to the technological wonders of the James Webb Space Telescope showcases the constant development of how we interpret the universe. It uncovered the vastness of space and changed fundamental ideas in astronomy. Take the Hubble Space Telescope HST, for example, it captured the iconic pillars of creation image in the Eagle Nebula revealing a star nursery formed by massive columns of gas and dust. Another significant achievement was the Hubble Deep Field capturing a vast number of galaxies in a seemingly empty patch of space. The HST also delved into exoplanet atmospheres, pinpointing elements like water and organic molecules in distant worlds, hinting at the possibility of habitable zones beyond our solar system. Following the development of the closest observed supernova SN 1987A, it shed light on the life cycle of massive stars. These achievements cemented the Hubble Space Telescope's legacy as a cornerstone of modern cosmology, dazzling the world with its incredible discoveries. Its successor, the James Webb Space Telescope, was launched to build on the technological advancements and lessons learned from a model of our understanding of the universe's origins, which today is explained by the prevailing theory of the universe's origin. Around 13.8 billion years ago, the universe began as an extremely hot and dense singularity, rapidly expanding and giving rise to matter, energy, and fundamental forces. As the universe expanded, it cooled, leading to the formation of atoms, stars, galaxies, and the various structures observed today. The Big Bang Theory also explains cosmic microwave background radiation, light element abundance, and the large-scale structure of the universe. Despite being widely accepted now, the Big Bang Theory faced skepticism and challenges. In its early days, alternative models, like the steady-state theory, proposed the universe without a specific beginning and concerns about evidence supporting the initial singularity expansion and observed anomalies arose. Most of these objections were addressed over time, and a significant piece of evidence came with the detection of cosmic microwave background radiation in 1965, aligning with the Big Bang prediction. Space missions like COB and WAP, along with technological advancements, further supported the theory. Accurate measurements of cosmic microwave background radiation aligned remarkably well with theoretical forecast. Enter the James Webb Space Telescope, equipped with advanced infrared instruments that can peer through cosmic dust. The JWST, working primarily in the infrared range, captures the oldest light in the universe and observes objects formed shortly after the Big Bang. Its infrared capabilities allow it to focus on star-forming regions, celestial nurseries, and the formation of stars hidden from optical telescopes. Infrared light with longer wavelengths compared to visible light can penetrate interstellar dust, overcoming a limitation of the Hubble Space Telescope. The JWST can observe cooler objects emitting mainly in infrared, making it ideal for studying phenomena like exoplanets, brown dwarfs, and distant galaxies. As celestial bodies recede, their emitted light waves are stretched, causing a shift toward longer wavelengths, a phenomenon known as red shift. The JWST infrared capabilities can detect these redshifted signals, capturing light from the early universe and offering insights into its formation and evolution. Energetic events like black hole mergers or new star births primarily emit in the infrared range, further expanding the JWST. Investigative capabilities. The telescope can explore phenomena that would otherwise be hidden or invisible. The JWST complements optical telescopes like Hubble by having enhanced sensitivity and the ability to detect infrared radiation. This ability allows it to peer further into space and delve deeper into astronomical history, revealing hidden astronomical wonders and providing a more comprehensive view of the universe's development. The JWST serves as our window into the earlier phases of cosmic evolution. Recently, it revealed something so astounding that it might prompt a reconsideration of the entire cosmological model of the universe. We've discovered enormous masses of galaxies at the very edge of the observable universe. These ancient galaxies existed just a few 100 million years after the Big Bang, during the cosmic dawn. The puzzling part is that we're unsure about how such enormous structures formed so early in the universe's history. This discovery might lead us to reconsider our understanding of the formation and Evolution of galaxies in the early universe. Studying early galaxies is crucial for unraveling the mysteries of cosmic origins. The JWST can gain insights into how galaxies, stars, and planetary systems arose and evolved over billions of years. These observations also contribute to broader questions about the fundamental nature of the universe, including its composition, structure, and the forces governing its evolution. While the Hubble Space Telescope was groundbreaking for its time, it had limitations in observing the early universe. Its main limitation was its inability to effectively penetrate cosmic dust and detect the infrared light emitted by ancient galaxies. Older telescopes relied on visible and ultraviolet light observations, making it challenging to explore the early universe where these wavelengths are absorbed or distorted by interstellar dust and gas. The James Webb Space Telescope presents a significant leap forward in observing galaxies from the universe's early stages. Unlike its predecessors, the JWST can observe celestial objects that formed within a few hundred million years after the Big Bang. Using its infrared sensitivity and advanced imaging capabilities, the JWST has uncovered an abundance of ancient galaxies, offering remarkable clarity and detail in understanding the universe's evolutionary history. Preliminary results from JWST observations have stirred waves in established cosmological models. The detailed data challenges several aspects of prevailing theories, prompting cosmologists to reconsider fundamental principles governing how we understand cosmic evolution and structure. Discrepancies between observed data and theoretical predictions have sparked intense debates within the scientific community. JWST observations have revealed a larger number of galaxies in the early universe than anticipated by existing models, suggest a more complex and rapid evolution process. Some observed early galaxies appear more developed than expected, challenging conventional models, predicting slower development. The discovery of an unfathomable mass of galaxies challenges the assumed distribution and arrangement of large structures, revealing a more intricate and denser cosmic web than previously thought. These observations raise fascinating questions and avenues for further exploration. The existence of large structures challenges early models of cosmic structure formation, prompting researchers to refine models for a better explanation. Understanding how such vast structures gathered rapidly after the Big Bang presents a puzzle that requires an explanation that doesn't violate fundamental principles of cosmology. Significant disparities in the conditions of the early universe compared to predictions based on existing models have also been revealed. These differences could suggest previously unknown physical processes, unexpected conditions, or unidentified cosmic phenomena. In simple terms, these variations have prompted scientists to rethink and improve our models of the universe. Currently, all we can do is say that further exploration is required to incorporate these surprising observations into a more comprehensive understanding of the universe. Initial observations often provide exciting glimpses into the universe, but in-depth investigations sometimes reveal differences. For example, early observed may show specific properties or arrangements within distant galaxies that upon closer examination reveal fluctuations in their composition, structure, or evolutionary pathways. In conclusion, enormous phenomena are incredibly complex and require careful investigation for us to accurately understand their true nature. Spectroscopy, a method that helps unravel the properties and history of celestial objects, is an example. It involves analyzing the light emitted or absorbed by astronomical objects. By examining the properties of the light, spectroscopy provides detailed information about the chemical composition, temperature, density, and movement of celestial bodies. This analysis helps us understand the origins, development, and contributions of celestial bodies to the cosmic tapestry. The JWST has uncovered numerous cases where initial observations differed from later investigations. For instance, initial observations of distant galaxies suggested a simple structure primarily dominated by lighter elements like hydrogen and helium in line with theoretical expectations, however. Spectroscopic analysis using the JWST showed fascinating variations in elemental signatures identifying heavier elements or compounds previously undetected or misunderstood in the early universe. This challenges conventional ideas about the early universe's chemical composition and the mechanisms responsible for their development and dispersion across vast distances. Similarly, initial assumptions about galaxies in the early universe were based on preliminary observations, suggesting a relatively uniform pattern of development and organization. However, more detailed investigations by the JWST revealed a much more diverse and complex array of chemical compositions within these galaxies. The James Webb Space Telescope continues to redefine our understanding of the cosmos by shedding light on previously hidden corners of the universe. One of its most exciting capabilities is its ability to study exoplanets in unprecedented detail by analyzing the atmospheres of planets orbiting distant stars. The JWST can detect crucial chemical signatures such as the presence of water vapor, carbon dioxide, methane, and other organic compounds. These findings provide valuable insights into the potential habitability of exoplanets and the conditions that might support life beyond Earth. In addition to exploring distant worlds, the JWST is transforming our understanding of star formation. It can observe the birth of stars in regions where young stars are surrounded by dense clouds of gas and dust which optical telescopes cannot penetrate. With its ability to detect infrared light, the JWST captures the faintest glimmers of these new stars as they emerge from the darkness, offering a clearer picture of the processes that lead to star and planetary system formation. By studying these regions, astronomers are gaining a deeper understanding of how stars like our Sun come into existence and evolve over time. Another remarkable aspect of JWST research is its ability to peer into the hearts of galaxies. Black holes, particularly supermassive ones, are believed to reside at the centers of most large galaxies. JWST's advanced instruments allow scientists to observe the behavior of matter around these black holes, providing new insights into their growth, their influence on galactic evolution, and the powerful jets of energy they emit. These findings are helping astronomers piece together the story of how galaxies and their central black holes evolve together, influencing each other's growth. Moreover, the JWST discoveries are not only answering long-standing questions, but also raising new ones as it probes deeper into the history of the universe. It is uncovering phenomena that challenge existing theories and models. These challenges drive the scientific community to refine current cosmological models and open up new avenues for research that were previously unimaginable. The discoveries of the JWST are not just pushing the boundaries of what we know, they are helping to reshape the fundamental principles of how we view the universe itself.